Have you ever stopped to think about shadows? They seem so simple, yet they hold fascinating secrets about our universe. Shadows are like whispers of light, telling tales of objects hidden and mysteries yet to be solved. From the everyday shadows we make with our hands to the cosmic shadows cast by planets and stars, they are everywhere, shaping our reality in ways we often take for granted. Think of a sunny day. You see your own shadow stretching out before you. It's a constant companion, mimicking your every move. But have you ever wondered why it changes shape? Why is it sometimes long and skinny and other times short and stubby? It's all part of the intriguing dance between light and darkness. Shadows aren't just about absence. They're about interaction. They tell us about the shape and size of objects. They tell us about the source of light. They even tell us about the vast distances of space and the strange objects that lurk within it. So let's embark on a journey into the world of shadows, where we'll uncover the secrets they hold and explore how they illuminate the mysteries of our universe. We all know how to make a shadow. Stand in front of a light source, and voila! Your shadow appears. But how exactly does this happen? Why does light seem to disappear behind an object, creating a dark area? The answer lies in the way light travels. Light travels in straight lines like tiny little photons on a mission. When these photons hit an object, they can't just pass through it. Some are absorbed by the object and some are reflected. The reflected ones are what allow us to see the object. Now imagine a straight line of photons heading towards you. You're standing in their path, blocking their journey. The photons hit you, and they can't continue on their straight path. This creates an area behind you where the photons can't reach. Your shadow. It's like playing a game of light tag. The light is it, and it has to travel in straight lines. You're the obstacle, preventing the light from reaching the area behind you. And that, my friends, is how a shadow is born. So, we know shadows are formed when light is blocked by an object or a person. But did you know that not all shadows are created equal? They can vary greatly depending on the light source and the object casting the shadow. Some shadows have different shades or zones within them, creating a fascinating play of light and dark. This is where the concepts of the umbra and penumbra come into play, adding depth and complexity to the shadows we see. Imagine standing under a bright spotlight with the light source directly above you. Your shadow on the floor is sharp and dark, with well-defined edges. This dark central region is called the umbra, the area of total shadow. It's the area where the light source is completely blocked by you, allowing no light to pass through. But now imagine there are two spotlights shining on you from slightly different angles, creating a more complex shadow. The shadows from each light source overlap, merging to form a new pattern. In the overlapping region, some light from one spotlight reaches the ground, while some light from the other spotlight is blocked, creating a mix of light and shadow. This creates a lighter, fuzzier shadow zone around the umbra, called the penumbra, where light is only partially blocked. This play of umbra and penumbra is what gives us the different phases of a solar eclipse, a spectacular celestial event. When the moon passes between the sun and Earth, it casts a shadow on Earth, creating a dramatic display. If you're standing in the umbra, you experience a total solar eclipse. The sun is completely blocked and day turns to night. But if you're in the penumbra, you'll see a partial solar eclipse. Only part of the sun is obscured, creating a partial shadow. Section 4. Quantum Shadows, where light plays hide and seek. Now let's dive into the realm where shadows get really weird. The quantum world, a place where the rules of classical physics no longer apply. Here, things aren't always as they seem. The behavior of particles and waves defies our everyday experiences. Light, which normally travels in straight lines, starts acting more like a wave, and shadows start revealing the strange and counterintuitive nature of reality. This duality is at the heart of quantum mechanics. Imagine shining a light through two tiny slits close together. This simple setup leads to astonishing results. You might expect to see two bright lines on the screen behind the slits, right? Just like how shadows form in our everyday world. Well, that's not what happens. The results are far more intriguing. Instead, you see a pattern of alternating bright and dark bands, an interference pattern. This pattern is a hallmark of wave behavior. This is the famous double-slit experiment, and it blew everyone's minds because it showed that light can act like both a wave and a particle. This dual nature is fundamental to understanding quantum mechanics. Even weirder, if you try to observe which slit the light goes through, the interference pattern disappears, and you're left with just two bright lines, as if the light knows it's being watched. This phenomenon is known as the observer effect. This experiment reveals a fundamental principle of quantum mechanics. Observation affects reality. The act of measurement changes the outcome. The very act of observing the light changes its behavior. This interplay between observation and reality is a cornerstone of quantum theory. And shadows, in this quantum realm, become more than just areas of darkness. They become tools for exploring the fundamental nature of light and reality itself. They help us understand the mysterious and fascinating world of quantum mechanics. Section 5. Shadows in the Cosmos, the Case of Black Holes. Let's journey now to the vast expanse of space, where shadows take on a whole new level of awe-inspiring power. The cosmos is filled with wonders, but few are as mysterious and captivating as black holes. Here, we encounter one of the most enigmatic objects in the universe: black holes. These cosmic giants challenge our understanding of physics and the nature of reality itself. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. This immense gravitational pull is what makes them so fascinating and terrifying. They are formed when massive stars collapse at the end of their lives, creating a singularity, a point of infinite density. This process is a dramatic and violent event, marking the death of a star and the birth of a black hole. Now, because no light can escape a black hole, we can't actually see one directly. They are invisible to our eyes and our telescopes. They're invisible to our telescopes. However, their presence can be inferred through indirect observations. But we can detect their presence by observing the shadows they cast on their surroundings. These shadows are like cosmic fingerprints revealing the hidden black hole. As matter falls into a black hole, it forms a swirling disk of superheated gas called an accretion disk. This disk emits intense radiation, making it one of the brightest objects in the universe. The intense gravity of the black hole warps the space-time around it, causing light from the accretion disk to bend and distort, creating a dark silhouette, the shadow of the black hole. This warping effect is a key signature of a black hole's presence. By studying these shadows, astronomers can learn about the properties of black holes, such as their mass and spin. This research helps us understand the fundamental laws of the universe. It's like using a cosmic shadow puppet show to unravel the secrets of these gravitational behemoths. Through these studies, we continue to push the boundaries of our knowledge and explore the mysteries of the cosmos. Section 6. Shadow Detectives, Finding Alien Worlds. Believe it or not, shadows aren't just useful for studying objects within our own solar system. Astronomers use shadows to hunt for planets orbiting distant stars. Exoplanets. One way to find exoplanets is to look for the tiny dip in a star's brightness that occurs when a planet passes in front of it, blocking a small amount of its light. This is called the transit method. Imagine a distant star as a giant spotlight shining across the vastness of space. Now imagine a tiny planet like Earth passing in front of that spotlight. From our perspective, the planet would create a minuscule shadow, causing the star's light to dim ever so slightly. By carefully measuring these dips in starlight, astronomers can infer the presence of an exoplanet. They can even determine the planet's size, orbital period, and distance from its star. It's like playing a cosmic game of hide-and-seek, using shadows to reveal the hidden worlds orbiting other stars. Section 7. The End. Or is it just the beginning? As our journey through the world of shadows comes to a close, we realize that these seemingly simple phenomena hold profound implications for our understanding of the universe. From the everyday shadows we cast with our bodies to the cosmic shadows cast by black holes, they reveal the secrets of light, gravity, and even the quantum nature of reality. So the next time you see a shadow, take a moment to appreciate its beauty and the science behind it. Shadows aren't just about darkness. They're about the interplay of light and matter, about the fundamental forces that govern our universe. They are reminders that even in the absence of light, there is knowledge to be gained and mysteries to be explored. The universe is full of shadows, each one holding a story waiting to be told. It's up to us, the curious explorers of the cosmos, to unravel their secrets and shed light on the wonders they conceal.